When we talk about probability distributions, a very important theme is also distribution testing. And distribution testing is important for two reasons. First of all, many modeling approaches rely on assumptions about data or assumptions about model error. That assumption is quite commonly normality, but not only. And the reason is that only using that assumption of, for instance, normality, when we get results, we can conclude or we can make inference about how good or bad the model is. And so, for instance, if we get error from our model and we test whether it's normal or not, only when knowing the answer, we can be sure that we can proceed and make some conclusions from our data modeling. Second thing is comparing two samples. So, of course, you could go simply with just checking. If you have two data samples, you want to check do they have the same mean value and the same standard deviation, and that's it. But if you want to be more precise, it's better to check whether they actually come from the same shape distribution rather than just having the same moments. So the most common tests for testing distributions are actually non-parametric tests. So it means they don't rely on model parameters, but they do rely on the sample itself. And they refer to data cumulative probability function or cumulative distribution function. So the two tests, with being Kolmogorov-Smirnov and Kramer-von Mises, they do talk about the direct relation between the empirical cumulative distribution function and the theoretical one. So the red one is the one we want to test for, and the blue one comes from data. Just a recap, cumulative distribution function, commonly denoted with capital F, is basically an integral from minus infinity to t of the probability that our random variable will take values less than t. So if a PDF has this shape and then we mark the t somewhere and we keep moving the t around, so then CDF for that particular t will be shaped roughly like this. If we talk about continuous distribution, it is actually approaching 1 when t goes to infinity. In discrete cases, for instance, when we roll a die and we have the 6 possible outcomes, then CDF would be looking in this discrete way. So each next value is bigger by 1/6, and then the final value is exactly 1. So for discrete distributions, we do have this 1, and for continuous ones, not always we are reaching exactly 1. For instance, for uniform distribution, yes, we would, because then it looks like this. So Kolmogorov, Smirnov, and Kramer-von Mises, they do this comparison directly of the empirical and theoretical CDF. They just have different formula for doing that. Anderson-Darling is very similar, but what it does, it first inverts the empirical cumulative distribution function. And the inverse should come from uniform distribution. So then it basically compares how much that inversed one is close to theoretical uniform distribution on interval 0 to 1. And I focus on these three tests because they are the most common and they are also available in MATLAB. So let's have a look at a couple of examples in MATLAB. The Kolmogorov-Smirnov test comes by the name Kay's test and Anderson-Darling by the name AD test. And from both of these you can get the hypothesis result, so whether we accept null, that should bring 0, or whether reject it, then it's 1. And then the p-value for that. And now I'll generate normally distributed random numbers, and these ones will come now from distribution with mean value 1000 and standard deviation 1. So I have rescaled it in here. Now the trick in here is that Kolmogorov-Smirnov actually always tests for normality, but for the standard normal distribution. So if I ran it now, even with big sample, it would actually reject normality, but it actually rejects the standard normality. So if I rescale my data by the mean value, then it should actually accept it. So let's see, we run this piece. And so we have now accepted normality from both tests. So this was Kolmogorov-Smirnov and Anderson-Darling. And if I didn't have this rescaling here, probably this one will fail, most likely, because the mean value is so far. Yes, so you can see it's very clearly, the p-value here is 0, so it's very clearly rejected normality, but the reason is that it's comparing to the standard normal. And Anderson-Darling just compares to normal distribution closest by the parameter values to our data. But of course, sometimes you may want to test for other than normal distribution, and you can also do it using those two tests. So for instance, I would like to check if the data I have generated is actually coming from Weibull distribution. So what I can do, I can get the estimates of Weibull parameters from my data. So I use it using this Weibull fit function. There are many of these kind of fit functions for other distributions. You can look them up from help. And then I need to build the empirical CDF. So what I do, for every x value or for the x range of my data, then I build CDF for those same values. So CDF is a ready function in MATLAB as well. You just say for which distribution you want your theoretical CDF. Then you give the x values for the range, and then you bring the parameter values which you want to be the closest to your actual data. And of course, different distributions have different number of parameters. There may be distribution with just one, with two, or three, or four. So that you can also look up from help when you check for CDF. And then how we use KS-test, for instance, is that we call KS-test, then we give our sample, and then we say that we want to use CDF as the method for comparison, and we give the test CDF. So this is now the theoretical CDF to which we want to compare our data. So let's run this part. And now normality is clearly rejected. We had quite a big sample here, but if we used actually something small, like just 20 numbers, it could happen that we will get this hypothesis accepted because the sample is relatively small, and Weibull distribution in some cases can actually look like closely shaped to normal.